Tonight, we're going to explore the most final event in all of existence. Not a war, not a supernova, not even the death of a star. Something quieter than all of those. Something so gradual that no civilization could witness it happening, and yet so absolute that nothing in the universe survives it. The last photon. A single particle of light, born from the cooling embers of the universe's final stars, traveling through an expanding void that has become so vast, so cold, so utterly empty that no eye exists to receive it, no detector, no atom warm enough to absorb it, and when it finally disperses its last fractional whisper of energy into the surrounding darkness, the universe will have experienced something it has never experienced before. Total darkness, forever. By the end of tonight, you're going to understand the exact sequence of events that leads to that moment, how the stars die, how the galaxies go dark, how even black holes eventually evaporate, how the universe cools toward absolute zero and never quite arrives, and why that last photon represents not just the death of light, but the final punctuation mark at the end of 13.8 billion years of cosmic history. Before we get started, if these questions about deep time and the ultimate fate of everything keep you up at night the way they keep us up at night, hit like or subscribe. It helps more curious minds find us. Now let's begin. The year is 13.8 billion years ago. The universe is hot, incomprehensibly, violently hot. In the first fraction of a second after the Big Bang, temperatures exceed anything that exists anywhere in the modern cosmos. The laws of physics as we understand them barely apply. Particles are being created and annihilated constantly. Matter and antimatter fight for dominance. For every billion particles of antimatter, there are 1,000,000,001 particles of matter. That tiny imbalance will determine everything. In the first 3 minutes, protons and neutrons fuse into the first atomic nuclei. Hydrogen, helium, a trace of lithium, nothing heavier. The universe is too hot for electrons to bind to nuclei. Photons scatter off the dense plasma constantly, unable to travel more than a tiny distance before being absorbed and re-emitted. For 380,000 years, the universe is opaque. Light cannot travel freely. The universe glows brilliantly, but nothing can see through it. Then the temperature drops to about 3,000 degrees Kelvin. Electrons combine with nuclei. Atoms form for the first time. The plasma becomes a gas. Suddenly, photons can travel. They stream outward in all directions, and the universe becomes transparent. That flash of light from the moment the universe first became transparent still exists today. We call it the cosmic microwave background radiation. It has cooled from 3,000 degrees to about 2.7 degrees above absolute zero. It's a photograph of the infant universe stretched and cooled by 13.8 billion years of cosmic expansion. Every microwave detector on Earth picks it up as faint noise in every direction. That ancient light is the oldest photon field in the universe, but it will not be the last. To understand the last photon, you have to understand what makes light in the first place. And to understand that, you have to understand stars. A star is a gravitational catastrophe in slow motion. Gravity wants to collapse it. Pressure from nuclear fusion wants to expand it. For most of a star's life, these two forces are in perfect balance. The star sits in what astronomers call the main sequence, burning hydrogen into helium at its core, radiating the energy of that fusion as light, heat, and other forms of electromagnetic radiation. Our sun converts about 600 million tons of hydrogen into helium every single second. It has been doing this for 4.6 billion years. It will continue for another 5 billion years, approximately, before the hydrogen in its core runs out. When the hydrogen runs out, the balance breaks. The core contracts. The outer layers expand. The sun becomes a red giant, swelling to perhaps 150 times its current diameter. Mercury will be consumed. Venus will be consumed. Earth will likely be consumed, or at minimum scorched to a lifeless rock. Then the helium at the core ignites. For a brief time, helium fuses into carbon and oxygen. Then that runs out too. The sun is not massive enough to ignite carbon fusion. The core collapses into a white dwarf, a dense ember about the size of Earth, composed mostly of carbon and oxygen, held up not by fusion but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy state. The outer layers are expelled into space as a planetary nebula, a beautiful, expanding cloud of glowing gas that will dissipate over tens of thousands of years. The white dwarf that remains is extraordinarily hot when first exposed, potentially 50,000 degrees Kelvin or higher. It shines with white light, but it has no fuel source. It is simply radiating the heat stored in its mass, and that heat will eventually run out. Over billions of years, the white dwarf cools. Its surface temperature drops. The light it emits shifts from white to yellow to orange to red. Eventually, it becomes what theorists call a black dwarf, an object no longer emitting any visible light, cold enough that it is essentially invisible. The problem is that the universe is not yet old enough for any black dwarfs to exist. The coolest white dwarfs currently observed are still around 4,000 degrees Kelvin. To cool completely would take longer than the current age of the universe by a factor of thousands or more. But we're getting ahead of ourselves, because before the last white dwarf cools, an extraordinary amount of cosmic history has to unfold. Right now, the universe is doing something it has never done before in its history. It is making stars faster than any previous era. That statement surprises most people. We tend to think of the Big Bang as the moment of maximum creation, the moment when everything began. But the Big Bang produced almost no stars directly. It produced hydrogen and helium gas. Stars came later, when that gas collapsed under gravity. The peak of star formation in cosmic history occurred about 10 billion years ago, roughly 3 billion years after the Big Bang. That era is called cosmic noon. Galaxies were forming rapidly, colliding, merging, feeding enormous reservoirs of gas into their central regions, igniting star formation at rates hundreds of times higher than what occurs in our galaxy today. Since then, star formation has been declining. The supply of cold gas that stars need to form has been gradually consumed or blown out of galaxies by stellar winds and supernova explosions. The universe is getting quieter. This matters because the timeline of the last photon depends entirely on when the last star forms, how long it lives, and how long its remnants glow. Here is the key insight that most people miss. Not all stars are created equal. The massive stars, the ones 10 to 100 times the mass of our sun, burn extraordinarily bright and die young. They live for only a few million years, then explode as supernovas, leaving behind neutron stars or black holes. They contribute enormous amounts of light while they live, but their lifetimes are cosmologically brief. The small stars, the red dwarfs, the ones with masses between about 8% and 50% of the sun's mass, are the opposite. They burn so slowly, so efficiently, that they will outlive every other type of star by enormous margins. A red dwarf with 10% of the sun's mass may live for 10 trillion years. That is more than 700 times the current age of the universe. And red dwarfs are the most common type of star. About 70% of all stars in the Milky Way are red dwarfs. Most stars in most galaxies are red dwarfs. They are dim, cool, hard to see individually, but they vastly outnumber every other stellar type. This means the future of starlight belongs to red dwarfs. Every massive star that ever existed or will ever exist will be dead long before the last red dwarf stops burning. The cosmic story of light is ultimately a story about these small, quiet, extraordinarily long-lived stars slowly burning down, one by one, over time scales that make the current age of the universe look like the first heartbeat of a very long life. To talk about what happens after the stars, we need a new unit of time. We're accustomed to thinking in years, millions of years, billions of years, but the time scales involved in the death of the universe require something more structured. Cosmologists use what's called the cosmic decade system, where each unit represents a power of 10 years. The current age of the universe is about 10 to the power of 10 years. We are in cosmic decade 10. The sun will die at roughly cosmic decade 10, approximately 5 billion years from now, give or take. Red dwarfs will continue burning until roughly cosmic decade 13 to 14. That's 10 trillion to 100 trillion years from now. During this era, the universe grows progressively dimmer. Massive stars are already gone. Sun-like stars gradually extinguish. The only light comes from the red, dim glow of red dwarfs scattered across an increasingly empty-feeling universe. During this era, the galaxies themselves begin to change. Star formation has nearly ceased. There isn't enough new cold gas to trigger the collapse that forms new stars. The galaxy is living off its existing stellar population. Old stars die and are not replaced. The Milky Way will have collided with Andromeda by around cosmic decade 11, about 4 billion years from now. The two galaxies will merge into a larger elliptical galaxy, which astronomers already have a name for: Milkomeda. This collision won't destroy stars directly. The distances between stars are so vast that actual collisions are vanishingly rare. But the merger will trigger new rounds of star formation as gas clouds compress and collide, a final burst of stellar birth before the long silence. By cosmic decade 13, even those stars are gone. The universe contains almost nothing but white dwarfs, cooling slowly, neutron stars spinning down, black holes growing as they absorb the rare stray atom or photon that drifts within their grasp, and the cold, dark remnants of red dwarfs that have finally exhausted their last reserves of hydrogen. The photons still exist at this point. White dwarfs still emit them, just in diminishing quantities and at longer wavelengths as they cool. The universe is not yet dark, but it is very, very dim. And then something strange happened. Around cosmic decade 15 to 37, a phenomenon that has never been directly observed will reshape the universe. Proton decay. The proton is the positively charged particle at the heart of every atom of ordinary matter. It feels stable. In experiments, physicists have looked for proton decay and found no evidence of it over observing periods of decades. Current experimental limits suggest a proton's half-life is at least 10 to the power of 34 years. But most extensions of the standard model of particle physics predict protons are not truly stable. Given enough time, even a proton will eventually decay into lighter particles, primarily a positron and a neutral pion, which itself immediately decays into two gamma-ray photons. If proton decay happens on a timescale of around 10 to the 34th years, then by cosmic decade 40, every proton in the universe that has not fallen into a black hole will have decayed. Every white dwarf, every neutron star, every cold rocky planet, every dust grain drifting through interstellar space will gradually dissolve into radiation and leptons. The universe will no longer contain any ordinary matter. This is a profound and almost incomprehensible transformation. The atoms you are made of, every atom in every rock and ocean and star in the observable universe, will have ceased to exist, not destroyed in any violent sense. Simply decayed, converted particle by particle into energy over timescales so vast that the transformation is imperceptibly slow even on cosmic scales. Each proton decay produces a tiny burst of radiation, a handful of photons. Those photons join the ever-diluting cosmic background, and then the radiation cools further as the universe continues expanding, the photons stretching to longer and longer wavelengths, their energy declining towards zero. But even after all ordinary matter is gone, one structure remains: the black hole. Black holes are the last strongholds of mass in the dying universe. They form from the cores of massive stars that collapse at the end of their lives. They grow by absorbing gas, dust, stars, and other material that wanders too close. The largest ones, the supermassive black holes at the centers of galaxies, contain masses equivalent to millions or billions of suns. For a long time, black holes were considered essentially eternal. Once mass falls into a black hole, it cannot escape. The escape velocity at the event horizon equals the speed of light. Nothing, not even light, can climb back out. Then in 1974, the physicist Stephen Hawking made a discovery that changed everything. He combined quantum mechanics with general relativity and found something unexpected. Black holes emit radiation, not from inside the event horizon, but from the quantum fluctuations at its surface. The mechanism is subtle. In quantum field theory, empty space is not truly empty. It is filled with pairs of virtual particles, particle and antiparticle pairs that pop into existence and almost immediately annihilate each other. This happens continuously everywhere in space, including just outside the event horizon of a black hole. Occasionally, one particle of a virtual pair falls into the black hole before the pair can annihilate. The other particle escapes. From the perspective of a distant observer, the black hole appears to have emitted a real particle. From the perspective of the overall energy balance, the black hole loses a tiny amount of mass to produce this radiation. Hawking radiation is extraordinarily faint for large black holes. The temperature of the radiation is inversely proportional to the mass of the black hole. A black hole with the mass of our Sun would have a Hawking temperature of about 60 nano-Kelvin, which is far colder than the cosmic microwave background and therefore completely undetectable against that background. It is also radiating slower than it absorbs energy from the CMB, so it is actually gaining mass, not losing it in the current era. But as the universe expands and cools, the CMB temperature drops. Eventually, the CMB temperature will fall below the Hawking temperature of even the largest black holes. At that point, the black holes begin losing mass faster than they gain it. Hawking evaporation begins in earnest. Smaller black holes evaporate faster. Larger ones take longer. The most massive supermassive black holes, those containing billions of solar masses, will take approximately 10 to the power of 100 years to evaporate. That is cosmic decade 100. To give you a sense of scale, the number 10 to the 100th power, also called a googol, is larger than the estimated number of atoms in the observable universe. We are talking about a duration so long that every proton in the universe decayed billions of times over before the largest black holes finish evaporating. But they do evaporate, and when they do, the final moments are dramatic. As a black hole loses mass, it gets hotter. As it gets hotter, it radiates faster. The process accelerates. In the final fraction of a second, the last remnants of a black hole release a final burst of very high energy radiation. A brief, brilliant flash from something that existed for almost incomprehensible eons. Then it is gone, and the universe, for the first time in its existence, contains no black holes, no star, no planets, no atoms, no protons, just a diffuse soup of electrons, positrons, neutrinos, and photons, all cooling and expanding in the dark. The photons that survive into this era are nothing like the photons produced by stars. A photon from the surface of our Sun has a wavelength of about 500 nanometers, right in the middle of the visible spectrum, which is why our eyes evolved to be sensitive to that wavelength. That photon carries enough energy to trigger a chemical reaction in a retinal cell to power the synthesis of a sugar molecule in a leaf to be detected by a photoelectric cell. In the far future, the photons that remain have been stretched by cosmic expansion to wavelengths billions and trillions of times longer than visible light. They are radio waves, then microwave radiation, then something for which we don't even have a common name. Radiation at wavelengths larger than the observable universe was in its early history. Their individual energies are almost unimaginably small. They carry almost no energy at all, but they still exist. They still travel at the speed of light, and they still interact in principle with matter, except there is no matter left to interact with. This is the cruel irony of the photon's existence in the dying universe. It still propagates. It still obeys Maxwell's equations and the principles of quantum electrodynamics. It still has a wavelength and a frequency and a direction of travel, but there is nothing to absorb it, nothing to scatter it, nothing to detect it. The photon does not experience time in the relativistic sense. From a photon's reference frame, it travels from emission emission to absorption instantaneously. The billions of years we see it crossing are zero from its perspective. But in this final era, the photon has no absorption event. It travels forever in a kind of temporal suspension from a relativistic standpoint, waiting for an encounter that will never come. A photon is both the most free thing in the universe and the most trapped. Free in the sense that nothing constrains its travel. It moves at the maximum possible speed through the cosmos. Trapped in the sense that it cannot stop, cannot change its speed, cannot choose a different direction without scattering off something. And in the late universe, there is nothing to scatter off. The photons just travel endlessly through an expanding void that grows larger and emptier with every passing eon. But to get to the last photon, we need to trace the specific sequence more carefully, because there are several distinct types of photons in the late universe, each produced by a different mechanism, each lasting for a different duration. The first to go are the photons from stellar fusion. These are the photons we think of when we think of starlight. Produced in the cores of stars by nuclear reactions, they bounce around inside stars for thousands of years before finally emerging from the surface and streaming outward into space. These photons end when the last star ends. The last star, the final red dwarf with just barely enough mass to sustain hydrogen fusion, will exhaust its fuel somewhere around cosmic decade 14. When it does, its core will contract into a helium-white dwarf, an object no larger than Earth, composed of nearly pure helium, radiating slowly cooling light into the void. For a brief time, cosmologically speaking, perhaps another trillion years, the universe still contains white dwarfs, bright enough to be called stars in the loose sense of the term. They emit light. They are hot. They are sources of photons. Then proton decay begins to affect them. The carbon and oxygen in white dwarfs, and eventually the helium, decays proton by proton over the vast spans of cosmic decade 30 to 40. The white dwarfs literally dissolve from within, producing a slow drizzle of gamma-ray photons as each proton decays. These are not the warm, friendly photons of visible starlight. They are high-energy gamma rays, product of matter annihilating itself according to the laws of quantum mechanics. Each of these gamma-ray photons redshifts quickly due to cosmic expansion. Within cosmological time frames, a photon produced by proton decay in a distant white dwarf will cool to infrared, then radio, then beyond, as it travels through expanding space. The photons from proton decay last until roughly cosmic decade 40. After that, no white dwarf remnants remain to decay. The source is exhausted. What photons remain after that point? Primarily, Hawking radiation from black holes. As black holes evaporate, they produce a thermal spectrum of photons covering a wide range of wavelengths. Smaller black holes, stellar mass black holes of a few to a few dozen solar masses, produce Hawking radiation at relatively higher temperatures, though still extraordinarily cold by any normal standard. They evaporate faster. Their contribution to the photon field ends first, somewhere around cosmic decade 67 for a solar mass black hole. The supermassive black holes hold out longest. The black hole at the center of the Milky Way, which currently masses about 4 million times the Sun, will evaporate over approximately 10 to the 87th years. The largest known black holes, those found at the centers of the most massive galaxies, clocking in at tens of billions of solar masses, take the full 10 to the 100th years to evaporate. Each of those final evaporation events is a brief flash of radiation, the last gasp of a gravitational giant that has been slowly consuming the universe for eons beyond eons. For an instant, the temperature of that region spikes. A burst of high-energy photons radiates outward. Then nothing. After cosmic decade 100, the last black hole has evaporated. The photon population of the universe now consists entirely of the ancient, cold, stretched photons from all previous eras, red-shifted to wavelengths so long they carry almost no energy, plus the brief final emission from the last black hole's death. And then those photons keep traveling through a universe that is expanding exponentially faster than they can traverse it, through a void where the average distance between photons grows larger every moment, through a darkness so complete that the photon field itself, though technically present in some regions, is for all practical purposes non-existent. This is perhaps the most sobering part of the entire story. The last photon will travel through a universe with no observers. For a photon to be detected, it must encounter something capable of absorbing it. In the early universe, that meant atoms, molecules, gas clouds, eventually eyes and instruments. But in the late universe, after proton decay and black hole evaporation, there are no atoms. There are electrons and positrons, leptons and neutrinos, and the photons themselves. Could an electron absorb a photon? Yes. Compton scattering is a real process. A photon can scatter off an electron, transferring some energy and changing direction. But in the late universe, the electron density is so vanishingly small, and the space between particles so incomprehensibly vast, that such encounters are extraordinarily rare. Could an electron and a positron annihilate to produce photons, and could those photons subsequently be absorbed by another electron-positron pair? In principle, yes. But the particle density is so low and space is expanding so rapidly that the probability of any two particles encountering each other becomes, over cosmological time, effectively zero. Life, as we understand it, requires chemistry. Chemistry requires atoms. Atoms require protons and electrons. Protons are gone by cosmic decade 40. The last life possible in the universe, if any such thing could exist using unconventional mechanisms, would cease long before the last photon is emitted. Any civilization, any intelligence, any consciousness that arose in the universe would be restricted to an era when matter still existed. The latest possible era for mind to exist is likely sometime around the Hawking radiation phase, when black holes are still pumping out thermal radiation that could in principle power some exotic form of information processing. Some theorists have speculated about the possibility of intelligence persisting into these late eras, using black holes as power sources, using the temperature gradients between Hawking radiation and the ambient CMB to do thermodynamic work. But such speculation strains the limits of what physics permits. By the time the last black holes evaporate, even the most optimistic scenario for exotic intelligence has no energy gradient to exploit. There is no temperature difference, there is no disequilibrium. Everything is equally, uniformly, extraordinarily cold. The last photon, therefore, travels unobserved. It crosses a universe that has no means of perceiving it. It carries information about its origin in its wavelength and polarization and direction, information that encodes the event that produced it, but there is no decoder. No telescope, no detector, no retina, nothing. The photon does not know this. The photon does not experience anything. It has no consciousness, no awareness. But if it could be said to have a purpose, the carrying of information from a source to a receiver, that purpose has been permanently extinguished. It carries its message through a universe of no readers. Now let's talk about something that rarely comes up in discussions of the universe's end. The photon itself is thought to be completely stable. Unlike the proton, which theories predict will eventually decay, the photon has no known or predicted decay mechanism. It does not have a half-life. It does not turn into something else over time. A photon, traveling through perfectly empty space with no gravity or expansion effects, would travel forever, unchanged, undiminished. But space is not empty, and space is expanding. The expansion of the universe stretches photons. As a photon travels through expanding space, its wavelength increases, its energy decreases. This is the cosmological redshift. A photon emitted with enough energy to power a chemical reaction in a living cell will, after traveling across the observable universe for billions of years, arrive with an energy thousands of times less than it started with. The photon has not decayed. It has not turned into something else, but its energy has been drained by the expansion of space itself. The energy has gone, in the formal accounting of general relativity, into the work of expanding the universe, though this is a somewhat subtle statement about a curved space-time. In the far future, a photon emitted during a black hole evaporation event will redshift continuously as the universe expands. Its wavelength grows, its energy approaches zero asymptotically. In principle, the photon never reaches exactly zero energy. It just gets closer and closer. This means, in a precise technical sense, there may not be a single definable last photon event in the classical sense. Instead, there is a photon field that becomes increasingly dilute and increasingly low energy, approaching but never quite reaching zero. But for all practical purposes, at some point, the energy per photon becomes so small and the density of photons so low, and the distances between them so vast, that the universe is functionally dark. The last photon to be emitted, as opposed to the last photon to exist in any meaningful sense, will likely come from the final dying moments of the last supermassive black hole. Its evaporation burst, a brief flash of radiation from a singularity that has been consuming matter and radiating it away for nearly 10 to the 100th years. That burst will include photons across a broad spectrum, high-energy gamma rays in the final instant, lower-energy photons in the longer ramp-up to the final burst. Those photons will travel outward in all directions at the speed of light. They will encounter nothing. They will scatter off nothing. They will be absorbed by nothing. They will travel and travel and travel through a universe that grows larger and emptier with every meter they cross, their wavelengths stretched by the expansion to lengths that dwarf anything in the current universe. And eventually, each photon will have redshifted so thoroughly, its energy so decimated by billions and trillions of years of expansion, that it carries essentially no energy at all. The lights do not go out dramatically. They fade, so slowly that no observer could notice the dimming, even over millions of years. They just become less and less meaningful, less and less energetic, until the concept of the universe having a photon field becomes a matter of technically correct but practically irrelevant physics. But here is something extraordinary. Something that pulls us back from the abstract mathematics and reconnects us to the human story. Every photon that exists right now is part of this chain. every photon that left our sun this morning, every photon from a distant quasar that has been traveling for 12 billion years and just entered your window, every X-ray from a neutron star collision, every radio wave from the first moments of the universe, all of them are part of the same grand continuum that will ultimately end in the cold darkness. The photons you see right now, the ones bouncing off this screen into your eyes, were produced by electrical processes in a display, which got their energy from a power grid, which got its energy from burning fuel or splitting atoms or capturing sunlight, all of which trace back to energy released by nuclear processes in stars, which trace back to the gravitational collapse of gas clouds, which trace back to the Big Bang. The photon entering your eye right now is a direct descendant of the Big Bang, a particular channeling of the original energy content of the universe, passed from form to form, converted and reconverted, but never truly created or destroyed, just transformed and transferred. And the photons we emit, the light from our cities visible from space, the radio and television signals we have been broadcasting for a century, those photons are already out there. The first radio broadcasts from the early 20th century have now spread across a sphere over 200 light-years in diameter. Every photon from those broadcasts is still traveling, still carrying its encoded information outward at the speed of light. They will fade with distance. Their intensity drops with the square of the distance. By the time they reach even the nearest stars, they are extraordinarily faint. But they are there. They are part of the photon history of the universe. Those photons will still exist in some form when the last stars die. Their wavelengths will have stretched into the radio range beyond any detection. Their energies will be negligible, but they are real physical entities tracing a continuous line from a morning radio broadcast in the 1920s to the cold, dark, empty universe of cosmic Decade 100. Every photon tells a story, and the story of every photon ends the same way, not with destruction, but with diffusion, with redshift, with the slow, inexorable dilution of its energy across an expanding space until the concept of that photon having meaningful energy becomes a matter of philosophy rather than physics. Before we get to what this all means, we should address one remaining possibility. Quantum mechanics introduces an element of eternal uncertainty even into the heat-death universe. Even in a universe at maximum entropy, quantum fluctuations still occur. Particles and antiparticles still pop into existence from the vacuum. Tunneling events still happen. Energy can spontaneously concentrate in a small region by pure statistical chance. The Boltzmann brane scenario, first proposed in the context of statistical mechanics by Ludwig Boltzmann in the 19th century, imagines that given infinite or near infinite time, even in a maximum entropy universe, random quantum fluctuations will occasionally produce highly ordered structures. These would be extraordinarily rare, but not in principle impossible. A Boltzmann brane would be a self-aware entity that spontaneously fluctuates into existence from the thermal background, complete with false memories of a past that never happened, existing for a brief moment before dissolving back into equilibrium. It is a deeply strange concept, philosophically troubling, but mathematically consistent with a universe that persists long enough. If Boltzmann branes are real, then even after the last ordinary photon, there might occasionally be a spontaneous fluctuation that includes a photon for a brief moment. The universe would not be entirely without photons forever. It would occasionally, with vanishingly small probability, produce a photon-like fluctuation, which promptly dissolve. But this is a very different thing from the photons produced by stars and black holes. These would be vacuum fluctuations, not meaningful radiation from physical processes. They would carry no information about any external source. They would exist for a moment and vanish. If we define the last photon as the last photon produced by a meaningful physical process, the last photon with a traceable origin in a physical event, the last photon carrying real information about the universe as it was, then that last photon is the one we have been describing. The final whisper from the final evaporating black hole. And if we define it more loosely as the last event that could even loosely be called a photon, then the answer dissolves into the mathematics of quantum field theory and the debate over what constitutes a real as opposed to a virtual photon. A debate that may not have a clean resolution. Another question is about consciousness and the last photon. If consciousness is a physical process, as neuroscience strongly suggests, then consciousness requires physical processes. It requires chemistry, which requires atoms, which requires protons. Once proton decay occurs, consciousness of any form resembling biological awareness is impossible. Could some other form of information processing persist into the black hole evaporation era? Could there be minds that run on something other than atoms? Some theorists have speculated about the possibility, but the thermodynamic constraints are severe. Any information processing requires energy gradients. It requires the ability to do work. As the universe approaches equilibrium, the available gradients diminish. By the time the last black holes are evaporating, the temperature gradient between Hawking radiation and the ambient background is tiny. The amount of thermodynamic work available per unit time is vanishingly small. Even in the most optimistic possible scenario, with perfect efficiency and exotic substrates, the total amount of thought that can occur in the universe is finite. Not just finite in any one lifetime. Finite in the entire future of the universe. There is a calculable upper bound on the total number of bits of information that can ever be processed in our universe, given its current energy content and the second law of thermodynamics. That bound is enormous, but it is finite. We exist in a universe that can, in total across all time, think a finite amount, and we are using up some of those finite thoughts right now. Every conscious moment, every calculation, every dream, every conversation is drawing from a budget that is large but not unlimited. The last photon is the last expression of that budget in the domain of light, the last transfer of energy through electromagnetic radiation. After it, the budget is spent. The universe, which began in extraordinary brightness and complexity, ends in extraordinary darkness and simplicity. What does the existence of the last photon tell us about the nature of the universe? It tells us that the universe has a direction, not a spatial direction, a thermodynamic direction. Things move from order to disorder. Energy moves from concentrated to dispersed. Light moves from intense to faint. Structure moves from complex to simple. The universe moves from its birth in a state of low entropy to its end in a state of maximum entropy. This asymmetry, the arrow of time, is baked into the second law of thermodynamics. It is why we remember the past, but not the future. Why effects follow causes. Why broken glasses do not spontaneously reassemble. Why the light from stars spreads outward and does not spontaneously concentrate back into the star. The last photon is the final expression of this arrow, the universe's last meaningful act in the direction of increasing entropy. After that, entropy is at its maximum. The arrow of time, in a physical sense, has no more meaning because there is no more meaningful change. It also tells us that the universe is extraordinarily generous with light and extraordinarily brief in its generosity on cosmic time scales. The era of stars, from the first stellar ignitions several 100 million years after the Big Bang, to the death of the last red dwarf in about 100 trillion years, spans perhaps 10 to the 14 years. This sounds enormous, but compared to the timescale of the universe's full lifespan, if we define that as the point of maximum entropy, the stellar era is a brief flash, a cosmic morning, a fraction of an instant in the full duration of existence. We live in that morning. We are residents of the luminous era. Every photon we see is a gift from a universe that is temporarily, briefly, by cosmic standards, in the business of making light. There are questions this timeline raises that science cannot fully answer. One of them is about the nature of time itself after the last photon. Time in physics is not simply the ticking of a clock. It is defined by the occurrence of events, by the sequence of distinct physical states. When a photon travels, that is an event. When a particle decays, that is an event. When any physical process occurs, that is an event, and events define time. In the maximum entropy universe after the last photon, what events remain? In the classical picture, very few. Quantum fluctuations still technically occur, but they are so rare, so brief, and so energetically faint that the time between them grows incomprehensibly large. The concept of time starts to become ill-defined, not because time has ended, but because there is nothing to measure it against. Some physicists have proposed that in the final state of the universe, the very concept of time becomes meaningless. Not in a mystical sense. In the precise physical sense that time is a parameter measured by the rate of change of physical systems, and if no physical systems are changing in any meaningful way, the parameter becomes undefined. Others argue that time continues, in principle, even in the maximum entropy state. The laws of physics still apply. The quantum state of the universe still evolves, even if that evolution produces no macroscopically distinct states. Time continues. It just contains nothing interesting. This is a genuinely open question in physics, and it may be unanswerable, because any answer would require information about a state that is inaccessible to any observer within the universe. There is one more thing to consider before we close. Voyager 1, the spacecraft we talked about in a previous episode, is currently at about 159 astronomical units from the Sun, drifting through interstellar space at 38,000 miles per hour. Its instruments are dying. Its power is almost exhausted. In a few years, it will go silent, but it will still be there, still drifting, still carrying the golden record. The golden record with its sounds and images and greetings from a species that existed during the luminous era. In 40,000 years, it will pass within 1.6 light years of the star Gliese 445. In 10 trillion years, The last red dwarf stars will be dying. In 10 to the 100th years, the last black holes will evaporate, and somewhere in the universe, if the golden record has not been destroyed by collision or radiation by that point, it will still exist. A disk of gold-plated copper, chemically inert, carrying the imprint of music and images and greetings from beings who lived and thought and wondered during the brief, bright morning of the universe. It will be drifting in total darkness. No star nearby, no radiation energetic enough to cause chemical reactions, no warmth from any source, just a disk in the void carrying its message that no one will ever receive. There is something both devastating and magnificent about that image. Devastating because of the absolute finality of it, the isolation, the darkness. Magnificent because the record was made at all. Because beings who knew they were mortal, who knew their civilization was finite, who understood they were brief creatures in a brief luminous era of a finite universe, chose to reach out anyway, chose to make something and send it into the void, chose to say, "We were here." The golden record is a photon made of matter, a message encoded not in light, but in the grooves of a metal disk, and like every photon from every star, it carries information from its source outward into a universe that will eventually have no capacity to receive it. But it was made, it was sent, and the making and the sending matter. What does it mean that there will be a last photon? Not in the mathematical sense. We've covered the mathematics. But in the human sense, what does this timeline say about existence? The universe will have produced an almost incomprehensible amount of light over its history. From the first photons released at cosmic dawn, when the first stars lit up and burned away the fog of neutral hydrogen that had obscured everything for hundreds of millions of years, to the final burst from the last evaporating black hole. The universe will have been, for a long time, a place of extraordinary brightness and complexity. In a small region of that universe, on an unremarkable planet, orbiting an unremarkable star in an outer spiral arm of an unremarkable galaxy, a species arose that could see light, that had eyes, that built instruments to extend those eyes, that used those instruments to trace the photons of the universe back to their origins and forward to their ends. We are, in some sense, what the universe does when it uses photons to build structures complex enough to understand photons. We are not separate from the light of the universe. We are made from it. The energy in every chemical bond in your body was once carried by a photon. The energy that built the carbon and oxygen and nitrogen in your cells was released by nuclear fusion in stars, transmitted to Earth's surface by photons, captured by plants, and passed up the food chain. We are temporarily organized light, and we are organized light that has become aware of the fact that the light will eventually end, that in the incomprehensibly deep future, the universe will be dark, that the final photon will cross a void with no recipient, that the story of light, which is also, in a real physical sense, our story, will draw to a close. This knowledge is perhaps the most distinctive thing about our moment in cosmic history. We are alive in the era of maximum brightness, cosmologically speaking, close to the peak of stellar activity in the universe's history. The cosmos has never been more structured, never hosted more complex chemistry, never supported more vigorous photon production than it does right now, or did a few billion years ago. We have the privilege of looking out at a universe still blazing with starlight in every direction. We can observe galaxies at cosmic noon, when star formation was at its peak, using telescopes that capture photons that have traveled for 10 billion years to reach our detectors. We live in the bright chapter. Future eons will be dimmer. The red dwarfs will provide a soft, deep red glow for another trillion years. Then the white dwarfs' fading embers. Then the gamma-ray drizzle of proton decay. Then the faint thermal whisper of black hole evaporation. And then nothing. The fact that we can describe this timeline, that we can do the physics and trace the implications from known equations to cosmic endpoints, is itself a form of light. Not photons, but information. Understanding. A brief, astonishing flicker of meaning in a universe that will eventually lose all capacity for meaning. The end of the universe is not an explosion. It is not a collapse. Current physics suggests it is not a big crunch, where gravity reverses the expansion and everything falls back together. It is not a big rip, where dark energy grows so strong it tears atoms apart, though some models allow for this possibility. The most widely accepted scenario, the one consistent with current observations, is sometimes called the heat death of the universe, or the Big Freeze. In this scenario, the universe expands forever. Everything gets farther apart. Entropy, the measure of disorder in a physical system, increases to its maximum possible value. Temperature asymptotically approaches absolute zero. No gradients of temperature or pressure exist to do thermodynamic work. No chemical reactions can occur. No information can be processed. No structure can form. The second law of thermodynamics says that entropy can only increase in a closed system. The universe is, in all reasonable models, a closed system. Its entropy has been increasing since the Big Bang, driven by the growth of structure and complexity and the dispersal of energy. Eventually, entropy reaches its maximum. The universe reaches thermodynamic equilibrium. At equilibrium, nothing happens. Not because everything is frozen and motionless. The remaining particles, electrons, positrons, photons, neutrinos, still move, still carry kinetic energy proportional to the ambient temperature. But that temperature is the same everywhere. There are no hot spots or cold spots. There is no way to extract useful work from any difference in temperature because there are no differences in temperature. The universe becomes, in the physicist's term, a heat death. Not hot, extraordinarily cold, but dead in the thermodynamic sense that no further organization, no further complexity, no further work can be extracted from the physical state. In this regime, the last photons are themselves agents of the final equilibration. They carry energy from regions that are slightly warmer, in the vicinity of an evaporating black hole, to regions that are slightly cooler. They are the universe's final mechanism for spreading energy. And once the last one has done its work, or rather once the last one has redshifted into irrelevance, the equilibration is complete. Nothing changes after that, not because change is forbidden, but because there is nothing to drive it. This is the final silence, not the silence of an empty room where sound waves could still theoretically propagate if something produced them. The silence of a state where no process exists to create any wave of any kind, where information is not merely absent, but undefinable, where time itself, in the sense of a sequence of distinct physical states, ceases to have meaning because each successive state is identical to the last. Tonight we explored the ultimate fate of light itself. We traced the timeline from the luminous present to the cold darkness of the maximum entropy future. We followed the photons produced by stellar fusion, by proton decay, by Hawking radiation, from their moment of birth to their final red-shifted, energy-depleted crossing of an empty universe. We learned that the universe began opaque and became transparent, that it reached peak brightness approximately 10 billion years ago and has been slowly dimming ever since. That red dwarfs will maintain a faint glow for 100 trillion years, that white dwarfs will cool into darkness, that proton decay will dissolve ordinary matter over timescales of 10 to the 34th years and beyond, that black holes will evaporate by cosmic decade 100, the last of them releasing a final burst of Hawking radiation into the void. And then the photons from that final burst will travel through an expanding universe with no observers, red-shifting continuously, losing energy to the expansion of space, growing colder and more diffuse with every eon that passes, until, for all practical purposes, the universe is dark, not in an instant, not in a dramatic final flare, in a slow, patient, thermodynamically inevitable dimming, so gradual that no observer, had any existed, could have detected it happening in real time. The light simply fades and fades and fades, and the darkness that remains is complete. The universe that began with a hot, brilliant, opaque explosion of energy and matter will end in cold, dark, silent equilibrium, and in between, for an extraordinary span of time, it was lit up. It blazed with the light of hundreds of billions of galaxies, each containing hundreds of billions of stars. It produced chemistry and complexity and life and consciousness and art and science and wonder. It produced beings who could look up at the stars and ask what they were, who could trace the physics of light from emission to absorption, who could calculate the trajectory of photons across 13.8 billion years, who could sit in a comfortable chair and contemplate, with full understanding, the fact that every photon that reaches their eyes will someday have no eye to reach. The last photon will not be observed, but we who exist now in the bright morning of the universe have observed billions of them. We have used them to understand the cosmos. We have traced with them the shape of space and the history of time. We have built instruments to detect them from 10 billion years away, and instruments to track the ones that left this planet carrying our voices and music into the interstellar dark. The photon is the universe's most fundamental messenger, and the universe, in its generosity, gave us billions of years of messages to read. We are still reading them, and for now, the light is still on. Here is something that takes a moment to fully absorb. The universe is not just expanding, it is accelerating in its expansion. In 1998, two independent teams of astronomers studying distant supernovas discovered that the universe's expansion rate is not slowing down due to gravity, as had been expected. It is speeding up. Something, which we call dark energy, is pushing space itself apart at an accelerating rate. This has profound implications for the last photon. In a universe expanding at an accelerating rate, distant regions of space eventually move away from each other, faster than light can travel between them. There is a boundary, called the cosmic event horizon, beyond which events can never send signals to us regardless of how long we wait. That boundary currently sits at about 16 billion light years. Over time, as expansion accelerates, galaxies that are currently visible to us will cross that horizon and become permanently inaccessible. Their light will never reach us. For an observer in the far future, the observable universe will be smaller, not larger. Only the very local group of gravitationally bound galaxies will remain accessible. Everything beyond will have receded beyond the horizon. This means that the photons from distant events in the universe's history are already becoming permanently inaccessible to any observer. The light from a supernova that occurred 10 billion years ago and just reached Earth is the last communication we will ever receive from the region where that supernova exploded. Its neighborhood has crossed our horizon. Future photons from that region will never arrive. The cosmic event horizon is itself a kind of final photon machine. Anything beyond it is causally disconnected from us, as surely as if it were in a separate universe. The last photon to cross our horizon from any given region will have crossed it already, unbeknownst to us, and no new photon from that source will ever follow. For the purposes of the true last photon, the accelerating expansion means that most of the universe's photon content is already permanently beyond any observer's reach. Whatever photons are left in the local group, whatever Hawking radiation from the local cluster's black holes, whatever relic radiation from ancient decays, these are all that any observer could ever detect. And the observers themselves are long gone.